Hello again, this is Professor David Clough, and this is the second Python workshop or bootcamp, and you should already be quite familiar with the Python programming language. Hopefully you completed the first bootcamp workshop to get to this point, and now we're moving on. The focus of this workshop is going to be how to use Python to solve the typical numerical problems that arise in chemical engineering problem solving. And you can see our outline here. We just start with an overview of process modeling and then have a segment on models that are based on algebraic equations and solving them. A second segment that is based on models that are represented by ordinary differential equations in two categories. And then we have a brief segment on optimization using Python. And finally, one on regression or curve fitting. So that represents what we're going to do here. You have these PowerPoint slides in the form of a PDF available to you for later review. You also have access to many of the files that we use in this screencast so that rather than typing them in at times, you can actually just load them into the Spider editor and proceed as I do. So let's move on here. And talk about process modeling. Just to give an overall picture of this, and quite often as we go about this, we formulate a process model in terms of a set of equations based on fundamental principles, and then we need to come up with some basic data such as physical or chemical properties, and then we need to have operating conditions for the process, at what temperature or pressure or flow rates, etc. it's being operated. And then putting these three together, we proceed to apply numerical methods, in this case with Python, and come up with a prediction of process performance. Now, there's another stage to this which happens often in practice, and that we outline in a dashed line here. And that is where we have operating data. This may be in a laboratory from experiments. It may be from an operating process or pilot plant. And we're able to do a comparison between our model performance and actual operating data performance. These will usually not agree. They may be fairly close, but they may not agree. So we can go into a phase of model adjustment, and that may require statistical techniques such as nonlinear regression. And then we can go back and we can modify our process model so that the next time we come through this scheme, we have a better agreement between operating data and process performance. And for something like a manufacturing process, we may need to do this model tuning up, as it were, periodically as things shift with the process actual performance. Now, if we're just designing processes, we may not have operating data, and that's why we're left with a dashed outline around that particular phase. So as we look at process modeling, there's a whole laundry list of concepts and details that come to bear. And we just denote some of these. On the left are our balances based on fundamentals, material and energy, and applying thermodynamics, describing mass transfer or separations, reaction kinetics, and if we're simulating dynamic behavior of a process, then we get involved with control systems. The kind of equipment that we model is very varied, and the list is long, but some common categories are listed here with vessels, heat exchangers, in terms of fluid flow, piping, valves, and fittings, pumps and compressors. As far as separations go, columns, and then transformation with reactors, possibly solids handling with processes like crystallization and filtration. And when we're dealing with dynamic simulation, we get involved in specifying the instruments that are used to measure process performance. As far as numerical characteristics go, we have algebraic equations. These may be a single nonlinear equation or more than one, possibly sets of linear algebraic equations, occur quite often in staged processes. And then differential equations, ordinary differential equations, partial differential equations, which we do not treat in this screencast, and then finally optimization and curve fitting. It is possible that we have systems which are a combination of differential equations and algebraic systems. These are often called, in short, DAEs, all right? So we're going to consider a set of examples here to illustrate how we use Python to solve these general problems. And we'll just present a list here so you have an idea of what's coming. We're going to use a chemical equilibrium for our single nonlinear algebraic equation. We're going to use a simple absorber column for a set of linear algebraic equations. Then we'll deal with a set of nonlinear algebraic equations in computing an equilibrium of steam and water at different pressures and temperatures. And then we will move on differential equations and consider a batch reactor with a single reaction. And then we'll extend that to a batch reactor with multiple reactions. We get into optimization. We'll consider single factor optimization, and then involve multiple factors possibly with constraints involved. And then finally, when we get to regression, we will consider fitting data with polynomials, and then the general situation of regression. So let's start by looking at single algebraic equations and the kind of methods involved there. And the first two categories are separated. One is bracketing, where we start with estimates of the solution on either side of the solution. And there are two different techniques here that are common: bisection and false position. And then we consider open methods where only one initial estimate of the solution is required. And the most common of these is the Newton-Raphson method. And then a sort of a variation on that is the modified secant method. And then there is a very popular hybrid method which uses both bracketing and open methods. And that's called Brent's method, and we'll show you how to use that with Python. And then there's a circular scenario
which is called substitution, which can be implemented with something called the Weggstein method. I just make note here that with my co-author Steve Chapra, we have written a comprehensive text on applied numerical methods for engineers and scientists, and that using the Python language, and that's currently available. So let's start simple with single algebraic equations and bisection. And here we have an equation which we describe as f of x versus x, and we're showing what a plot of that equation would look like, and we're interested in the condition where f of x equals 0. So this intersection right here represents the solution that we're trying to determine. Of course, in most situations, we don't have plots like this, or we don't have the time to make plots and study them. But the idea of bisection is we pick an estimate either side of the solution, and you can tell in monotonic functions that this is the case when the function evaluation for one of these initial estimates is positive and the function evaluation for the other estimate is negative. If they turn out to be both the same side, we'd reach the conclusion that we don't have a solution surrounded or bracketed. And then bisection says that we use the next estimate being the midpoint between x1 and x2, and then we check the sign of the function evaluated at that new estimate. And in this illustration, it's the same as the sign here for x1. So for the next iteration of the method, this x mid becomes x1, as illustrated over here on the right. And then we continue the process, and we have another midpoint. Here, the f of x evaluation is negative, so for the next iteration, this will become the x2, and we gradually home in on the solution. And as you can see here, each time we iterate the method, here between x1 and x2, and then here x1 and x2, the interval that contains the solution is cut in half, and that's guaranteed. So if we run something like 10 iterations, the interval is reduced by a factor of 2 to the 10th, or 1024. And if we run 20 iterations, it is reduced by a factor of 2 to the 20th, which is a number a little bit greater than 1,000,000. So by running 20 iterations, we're guaranteed of narrowing this interval to 1/1,000,000th of its original width, and that will usually get us what we want in terms of a practical solution. So what we're going to do is we're going to pop over to Spider, and we're going to code a function that implements bisection. You can do that with me, and then we'll put that function to work, and on an example equation, actually the one that is represented by this curve here. So let's pop over to our Spider editor. And I'm going to start by putting in the import of the NumPy module, as I know that I'm going to need that down the way. And then we're going to define a function called bisect, which has a name for a function that will evaluate our equation, our f of x, and then has initial estimates, all right, for x1 and x2.
and I'm going to keep this as simple as possible here. And I'm going to start with an if test. If func of x1, times func of x2 is greater than 0. Now, if this is the case, it means that the function evaluations have the same sign, and we have not surrounded the solution, at least for a simple monotonic function. So in this case, we can just return, and if we want, we can put in some type of a message in the return. Could say whatever I want here, don't bracket the solution or whatever. And so that's a test we can run, and the return will get us out of this function immediately with an error message. Otherwise, we need to have a loop that homes in on our solution. So I will say for I in range 20, that's going to give me my predicted 20 iterations. And I'll say my current x mid is equal to x1 plus x2 by 2. And then I'll say if func of x mid times func of x1 is greater than 0. What that means is that those two function evaluations have the same sign. Then what I want for the next iteration is that x1 takes on the value of x mid. Now, if that's not the case, it means the other is the situation. So I can just use a simple two-way if here and do else x2 is equal to x mid. And then that will complete the loop. And it doesn't like this here because this should be a 2. Okay, I caught that. And then we're going to just return, for example, the last value of x mid as the answer. Okay? So we'll find out if I've made any errors here, but we're going to go on and test this now. So I'm going to define another function, which is my f of x. And I'm going to just return the result of a formula, which is np dot sine of x plus 2, that times np hyperbolic cosine of x, and then at the end, plus 2. Okay? So that's my function, and then what I need are what are my initial estimates, and so I'll recall that chart from a couple slides ago, or the last slide, and I'll say I'll start with x1 equal to 0. It likes to put in those extra words, and you can hit the escape key to get out of that. x2 is equal to 3, and then I can say x solution is equal to bisect of f, x1 and x2 as my initial estimates. So you see what happens is that if I've identified in the call to the function my f of x, and then when it's using this general argument func, it will substitute for that f when it needs to evaluate the function. And then finally down here I can say with a print and use a little bit solution is, and then in my curly braces, 0, maybe 6.4f, and then beyond that apostrophe, I can put in format, and then XSOLN, and that should print my solution. Okay, you see how that works? So it's going to go into bisect, and it's going to run it 20 times and try to come up with the solution that we noted on the chart. And so let's see how lucky we are and whether we can get that to work. Maybe just to be careful here, I will start out and do a save as, and give me a moment to search for the right folder here. Apologize for that. And I will just call this first bisect and save it. So in case there's some disaster or something, I have that saved. Now let's go ahead and run the function. And if you look over on the right here, it displays the solution as 1.8229. Okay? So that's how that's set up, and it's worked. And let's come back to the slides and see similar coding and see a similar result, and then we'll move on and we'll show you how to use an alternate method to solve this equation. Okay? So this, we had a result of 1.8229, and this was the curve. So if you look at the solution here between 1.5 and 2, you can see that that's the number that yields f of x equal to 0. So this is an expanded version of what I typed in as simply as I could. And it shows some good practices when you're creating a function for general use. And the first is including something called a docustring. And this is included usually right as a header on the function and is between triple quotation marks. Okay? And here we give a brief description. And it says the method is iterated maxit. Now, in this particular case, we defined a keyword variable argument called maxit as 20. And what that means is if the user doesn't specify this when they call bisect, they're going to get 20. But it would allow them to put in a different number if they want. So that's a feature that we've added here. And then we describe our input arguments, and then the output argument, it says or an error message if the initial guesses do not bracket the solution. And then down here, we very much have the same code, which I put in simply. I added a couple of words here to the error message, and then added comments in order to explain what each line of code in the function is doing. Now, this is pretty common when you're constructing a function for general use, and it's so that you or others can go in and look at the code and understand what's being done. All right? So if we move on, what we can see is what I described, and that is that the solution is 1.8229, which is what I showed on my code. Now, before I go on, what I would like to do is pop back over to the Spider editor And I'm going to come in and I'm going to put in initial guesses which do not bracket the solution. All right, and then I'm going to run it. And what happened here is that it had a problem printing out the result. Initial estimates are incorrect. It had a problem doing that because it wants to print out a numerical result. All right? So there are a couple different ways to shortcut this. I'll show you another in a moment. But just for the moment, if I comment out this statement and just put in print x SOOLN simply, and then try to run that, you'll notice that it says initial estimates incorrect, because it's applying its own formatting to x SOLN, whether it's a string result or a numerical result. Okay? So a little bit on that. All right. Now we're going to move on here, and we're going to use this method that is called Brent's method. All right? And I need to modify my code, my main calling code, to do that. So let me do some surgery here, and I'm going to add an import up here, and it's going to say from a module called SciPy. We haven't used that yet. Scientific routines in Python. All right, and a submodule called optimize. Import a particular function called brentq. That's Brent's method. Now what we're doing there is we're replacing our homegrown bisect method, which is perfectly good, by the way, with this more powerful Brent's method. All right, and the way Brent's method works is it tries to use one of the open methods like modified secant, and which converges very quickly. But the problem with modified secant is it can tend to be unstable, whereas like the bisect method is extremely stable, but it's slower. So as it tries to use an open method, if it gets into trouble, it switches over to a bracketing method and then tries to go back to the open method when it gets close to the solution. So it's sort of a neat hybrid between an open method and the bisect method. And we'll take a look at the open method with an example coming up. All right. So we put that in there. Now, instead of bisect here, then, we are going to put in brentq. All right. Now, you'll notice if we hover on that, it gives a bunch of information, including a reference on the method. And then we can, if we want, we can go back to our original setup here with x1 between 1 and 3. And then let me do a save as here so we don't wipe out our previous one. And I'll call it first brentq. All right. And then we will try to run that, and it gives the same solution. All right. So that's very simple. We haven't had to compose our own function as we did with bisect. We can use brentq, and it becomes somewhat more of a black box where we really don't know exactly what's going on inside. As you learn more about Python, you can learn that since it is an open source system, you can actually go in and you can find the code in the brentq function if you want to learn more about what happens inside. So let's pop back to our slides. And this shows the solution with brentq as we just illustrated it. And you'll note that I've given a file reference there where you can have a reference file on this from the files that were distributed. There's also another option when you want to know more about the solution details that is shown here. And you'll notice what we've done is we've added to the brentq arguments full_output equals true. And when we do that, it not only gives us the solution, but it tells us how many times it had to call the function, how many iterations, and then it gives the root to all the digits of significance, and not just the ones that we displayed here with our 6.4. So there you go. That shows you a couple of ways to approach things with bracketing methods or with the hybrid brentq method. Now we're going to go on and we're going to look at a specific chemical engineering example, and it's described in this slide here. And so this is a chemical equilibrium, which is for what is called the water-gas shift reaction. You can see here carbon monoxide plus water in equilibrium with hydrogen and carbon dioxide. All right, a very common gas phase chemical reaction, which equilibrium has to be computed. So the general situation we have for an equilibrium constant is the ratio, in this case, of the product or elements on the right, components on the right, over the concentration of those on the left as an equilibrium. And we note that this is generally a function of temperature at nominal pressures. And then we have a model for the equilibrium constant, all right, which is given here as a natural logarithm. And you'll notice that it's inverse in temperature in kelvins. So we set up a reactor problem where we have a feed which is not in equilibrium in terms of molar feed. These need to be obviously molar concentrations. And so we have kilomoles per hour of these four constituents going into an equilibrium reactor. And this is operating at 1200 Celsius and 1 atmosphere. And we want to know what the product flow rates would be. So then we come to, well, we need to set up a mathematical model for that. So we say there's going to be a shift of X moles per hour having to do with moving to equilibrium. Sorry, apologize for that. We had what we say is that the hydrogen, all right, on this side undergoes an addition shift. Now X could come out being negative, and the CO2 the same, because these are equimolar reactions. And in order to have that happen, we have to have the opposite shift on the part of the constituents on the other side. And then what we're doing is we're taking this relationship up here and we're moving the equilibrium constant to the left side of the equal sign so that our f of x is equal to 0. So now what we have is an equation in one unknown, and we want to solve for x, and then we want to solve for the product flow rates by applying x to our feeds, all right? So that's the kind of situation that we have. So what we're going to do first is we're going to try to generate a plot here of our function just to see what it looks like. It's not a bad thing to do when you can. Now, let's see if I can find this particular item. Okay. So what I do here is have my imports, but then I define a function which is my f of x. And for our given scenario of temperature of 1200, and then I just convert that to kelvins, compute my equilibrium constant using the exponential function, which is the inverse of the natural log, put in my feeds, and then compute what we want this to be equal to 0, but it won't be. So compute the error in the function. And then what I'm doing here is I'm coming out and I am making a plot of the error of the function versus x, and I'm taking x between 100 and 200 in terms of the shift in terms of kmols per hour. All right? And then what we're going to do, that'll give us a little bit of an idea of what we should do in terms of initial guesses or estimates. So I create a plot and add some labeling, and then we can run this and see what it looks like over here. And there's the plot. I think you can see that. And we're always focusing on where the function is equal to 0. And we can see that apparently it's equal to 0 around maybe 170 plus in terms of a value of x. And it gives us an idea pretty easily here that if we use initial estimates of 100 and 200, they will bracket the solution. So that is useful to us. And then, so we can come back to our slides, and that is illustrated here. And it uses a little circle to indicate where the solution is. And it duplicates the code that we just ran in Spider. All right. So the next thing that we want to do is we want to set up a function, all right, where we expand f of x here to be able to pull out the temperature and these feed rates as arguments in the function and not specify them within the function so that it is more capable or flexible. So here is what that function looks like. And you'll notice that we come in with an argument of x, but then we have extra arguments, all right? Now that's different because when we go to our routine to solve the equation, it's generally only going to want to have x, but now we have to supply this additional information and get it through so that it comes in here and we can calculate our error based on this just as we did before. So this introduces an idea of a pass-through argument, and we talked about that some in our first Python workshop, but this is a good illustration of it. So essentially, we're going to have a main script where we set the temperature and feed rates, 4 feed rates. We set our initial estimates of x1 and x2, and then we need to call a function like bisect or brentq, in this case, with our function, and then with our initial guesses, and then with these initial arguments so that they can make their way through to our function and we can calculate the function error. So that's a pass-through, and this shows the way that you do it with your code, all right? So let's come back and let's take a look at that code. It's a little bit longer in the Spider editor. So what we're looking for here is a file that's named water gas solve. So I open this, and this, as you can see, is longer because it doesn't fit in one screen. And what we have here, starting out, is importing NumPy and pyplot, and then our brentq, as we did before. And then we've got our function, as we showed on the slide, where the temperature in Celsius and our feed rates in kmol per hour are now arguments. And then down here, we've got our values for the feed rates. And then we're doing something special here where we're saying we would like to solve this problem for a whole range of temperatures so that we can see how this changes, how our output flow rates change as we move through a range of temperatures. So we use the arange function here, and as you may recall, it takes us from 500 to 1525 in steps of 25, but it does not include the last one, which means it stops at 1500. Okay? And we'll see this after we run it. We can look at it in the Variable Explorer. And then we could try to calculate ahead of time, but we can just count the number of items in this T array, all right, using the len function from Python. And then what we do is we start out with our answers as empty arrays, just with brackets with empty arrays, all right? And then we start with initial estimates for x, in this case 50 to 450, because the x is going to change each time for each different temperature. And then we do a loop for all of the n temperatures, and we come in and we calculate the solution using t sub I, starting with t0 and going up to tn minus 1. And what we do then is we append, all right, the x solution to the x array here. Empty array, each time through we add the solution to that and expand the x array, and then we also expand the product flows with the new result each time. So we're building out the array over the range of temperatures that we specify. And then finally down at the bottom here, what we do is we make a plot using different colors and labels for legend of our outlet flows, and then add the legend and X label and the product flow rate. So that's what that looks like. And then let's run this code. And this is the result that we get. So the result, as you can see in the upper right here, shows the entire range of temperatures. And for each of step of 25 degrees, we have solved for the 4 outlet flow rates. And we see the top one here is steam, the red one is hydrogen, the green one is CO2, and the magenta line is carbon monoxide. So we can see what happens to the equilibrium as we go through a very wide range of temperatures, okay? And this just shows you how we can take and go beyond just solving one simple equation. We've illustrated some extra features here, in particular the idea of passing some extra arguments through a built-in function like brentq using the args equals method of doing that. All right. Now, if we come back to our slides, this is the code that we already talked through, and it illustrates an important technique, and that is starting with empty arrays and then building the arrays using the append function out of NumPy. And the code is available in water_solve.py. And then this is a bigger rendering of the plot that we just created. So you can see the overall trends that are occurring as we move on through. All right. So that is the end of that particular example. Now what we're going to do is we're going to move on and we're going to consider how we obtain the roots of a polynomial. Now here we've got, as we show on this slide, we've got a simple polynomial in x to different powers, and there are a set of coefficients. So for an nth order polynomial, we have n plus 1 coefficients, which we index 0 to n. And that's useful indexing because it corresponds to the way arrays are indexed in Python. And we'll have n roots, and they are either going to be real or they're going to be complex roots where they occur in conjugate pairs alpha plus bj, alpha minus bj, where j represents square root of minus 1. So we've got an example here, and let's pop over and show the example in Spider. Let me get rid of a couple of these and open down here under polynomial, all right, something called polynomial example. And so I've got 3 examples, and they're very simple to put together. They use a function in NumPy called roots, which is similar to MATLAB, where we supply the coefficients in descending order, and then it solves for the roots, and then we can print or display the roots. So you can see I set up an example here of the polynomial that we had on the slide. And then I have another one which has coefficients 1, 1, and 1 that happens to have a complex conjugate pair of roots. And then I show another function here which we'll get to in a bit, but what it allows you to do is it allows you to put in coefficients, all right, and then just allow it to compose the polynomial and from the roots, all right. These are roots, and what it's going to do is compose a polynomial based on these 4 roots using the poly function. So let's run this and see what happens. We've got the roots for our polynomial up here are 7, 4, minus 2, and minus 1. All right. And then the roots of this one, you can see we have a complex conjugate pair, same real part of minus 0.5. And the complex part, the imaginary part, excuse me, is the same number but reversed in signs, plus and minus. And then finally, if we take our code and our roots and we use the poly function, it recomposes the coefficients of the original polynomial. So that illustrates that. Okay, so let us pop back here and just look at that and how that is put together. All right. And it doesn't show the poly function there, but that is shown on the next slide, which we'll get back to in a moment. All right. So let us, what we're going to do now is we're going to show how to evaluate a polynomial using different x's, how to evaluate it, and then make a plot. So let's come back over to Spider here, and let's open a function, a file that is called polynomial example 2. Okay, this is fairly simple code, but what we're doing here again is we are specifying our polynomial coefficients, but x in this case, we're creating an array from -3 to 8 and 100 evenly spaced values from -3 to 8 for x. And then we're using a third function from NumPy, which is called polyval, very similar in this case to MATLAB, where we put in the coefficients and we put in x, but in this case, x is an array, so it produces an array of results, and then we plot y versus x in a chart. Okay, fairly simple code. Let's run it. And the results look like that. And as long as we pick enough points, in this case 100, from -3 to 8, it gives us a nice continuous curve that we can look at. And then, of course, as we're looking at that and look across, at 0, we see 1, 2, 3, and 4 roots, which are the roots that we determined using the roots function. Okay? So let's come back to the slide and look at that. And this was the use of the poly function to start with roots and compose the coefficients. And then this is what we just illustrated with the polynomial example2 file of how to take a range of x's and use polyval in order to create corresponding array of y's and then plot y versus x, and we get the nice plot that you're looking at there on the right. Okay, so now what we're going to do is move on to multiple equations, and we're going to start with linear sets of equations. And there's just some background information here that is meant to be a reminder for you, a sort of a review, and that is that we're talking, whoops, let me back up here. We're talking about, in general, n equations in n unknowns, the unknowns designated here x1 through xn, and the equations shown starting with the first equation down to the nth equation. And that gives us a series of coefficients A, where the first index is the row number or equation number, and the second index is the unknown number. So 2, 2, second equation, second unknown. And then we can take these and represent them using matrix multiplication in a matrix format, and then just represent that in a compact form with a coefficient matrix cap A, an unknown vector of x's, of n x's, and then a set of constants B, n constants. Now, solving the equations, we can consider solving the equations using numerical calculations. One way to do that is to, sorry about that. One way to do that is to take this equation up here and pre-multiply both sides by the inverse of A, and that gives us an identity matrix here times x, which is essentially the same as x, and then A inverse times B, so we can compute the solution by computing the inverse of A and matrix multiply it by the B vector. Now we can do it that way, but numerically it is inefficient, and there are better algorithms for this that are based on techniques like Gaussian elimination, or another one that's called LU decomposition, where the L stands for lower triangular and the U stands for upper triangular. So there are more efficient methods available to us than just doing this calculation here. For small sets of equations, it won't make any difference practically to us which way we do that. So let us take a look at a simple example, all right? And let's pop over to Spider here. And let me start with an empty, get rid of that header, and we'll just put in our usual NumPy import, and then we'll start by defining an A array, and I'll make this 3, 2, 1 for the first row, -1, 3, and 2 for the second row, and 1, -1, -1 for the third row. So that would be A, and then B vector I will have as 10, 5, and -1. So that's what that looks like. And then what I will say is I want the solutions, and I will use NP dot linalg, which is a submodule in NumPy, dot solve, which is a function in that submodule, and A and B. And then I'll keep it simple, and I'll just say print X. It's fairly simple, huh? See if I got it right. Let's run it. So it didn't like it, so I must have something incorrect here. So let's see if it's happier if I create arrays here. It still doesn't like it. Oh, I see my problem. Didn't need to do that. There's a comma needed there. Forgive me for that. Even we make errors. So let's run this, and we get an answer of 2, 1, and 2. So that's the solution of those equations. We've got something different. 3, 2, and 1. Oops. The example I had 3, 2, and -1. -1, 3, 2. 1, -1, -1. 10, 5, -1. Let's run that again. I get -2, 5, and -6. Okay. Okay, we got through that. So let's pop back over and look at the slide. So these were what the equations looked like algebraically at the top. And then over to the right, you can see how we set them up in a matrix vector format. And then we really didn't need the MP array function in this case, but I put it in anyway. And then this shows the setup, and it shows the solutions. And then I just note at the lower right that the solve function is adapted from a numerical method routine called GESV, and it uses LU decomposition with partial pivoting. And that's just some explanation of the numerical method that's used here. Okay? So that shows the solution of sort of a set of linear equations which doesn't have any practical meaning. So let's move on and look at a simplified staged absorber column. And in this case, we have 6 stages or equivalent stages, and we have a liquid flow rate coming through. All right. And then we have a gas flow rate coming up through. And then we denote our stages 1 through 6. And our entry condition here as subscript 0, and our entry condition here as subscript 7, all right? And so on each of these stages, we have an equilibrium relationship, which we represent here for an absorber, a simple equilibrium relationship as linear. And then we specify L and G, and we specify X naught, the liquid feed concentration, and we specify Y7, the entering gas concentration. And then we can write a component material balance for each tray of the column, which essentially says that what we've got on the column in terms of what's exiting has to be equal to complete the material balance, the two entry streams. And then we can get rid of the y's here by incorporating our equilibrium relationship, and we end up with an equation for each tray, which involves the liquid X on the tray above, on the tray, and on the tray below. And so we've got that for each of our stages. And if we put that together, we end up with 6 different relationships, and then that the top and the bottom, one of the terms in the general equation becomes a known in terms of the entry value, and then we move the knowns to the right-hand side, and we end up with a set of 6 linear equations in 6 unknowns, and we have a constant vector on the right that has mainly zeros, but it has an item for the first equation and an item for the second. And then we gather some basic data, as we illustrated in our second slide of this presentation, and that is the equilibrium model. We use the B, or intercept, of the model as 0, and we use 0.7. And then our operating conditions, we have 20 moles per second for liquid and 12 moles per second for gas. And then we have our inlet concentrations, all right, for Y7 down here, and for X0 up here, all right? So that's the kind of thing that we have for our absorber. And what we're trying to do in absorption is remove our item from the gas stream into the liquid stream. So we would expect the liquid concentration to increase as it goes down through our column. Okay? So let us pop over to our Spider editor again. And we already have that, so I don't need that code. And so let's go to our file called absorber.py and open that. And we've got some code that shows how we put this example together. First, we've got our basic data, which we illustrated on that slide, number of stages being 6, flow rates, and then our inlet concentrations. These are mole fractions, and these are molar flow rates. So we've got, starting out with our coefficient matrix, we're just creating an array of essentially 6 by 6, and it starts out being empty with zeros, and also our B vector containing 6 elements which start out empty. And then what we do is we go into 3 for loops in order to set up the items in the A matrix. And the way we do this is a little bit interesting. The first thing that we do is we have a for loop I going 0, 2, and -1, and we do the diagonal elements, all right? The diagonal elements. And those, let's pop back and look at that. The diagonal elements are these, and they include a minus sign L plus GA all the way down for X1 through X6. So we pop back over and look at that, and you can see there's your minus sign, L plus GA. And then we go from I to N minus 1, all right? Now remember, N minus 1 for range is N is 6, so N minus 1 is going to be 4. And so we're going from 0 to 4, and we're doing GA. So if we come back over here, that's these elements here, all right? These elements here for our 6 equations using GA, and we don't have one for the last because these are the elements that are above the diagonal of the matrix. Notice the L's over here, all right? And then we do a loop which sets the L equal to that diagonal on the matrix below the main diagonal. And then finally, we allow the B5, the last element of B, to be minus G times Y in. Now, coming back, we don't have a minus L times X naught there because our inlet mole fraction is 0, and that becomes 0. Okay, and then we just come in and say, okay, we got our A and our B, now let's solve it. And once we get our X's, we can get our Y's by just multiplying A times the X's. The X's here represent an array of 6 X's. These are 6 Y's. And then we just create a stage number from 1 to 6 using A range. When you don't specify a third element of A range, it uses 1. So this says go from 1 to 7, but then don't take the last element. So it goes from 1 to 6. And then we create a plot based on our stage of our X mole fractions and our Y mole fractions, all right? And you can see with the X's here, we use just a line and a 0 or a little 0 for the marker. And here for the Y's, we use a dashed line and a square. And we set up and we include a legend with X, or coming over here with Y. And then we put on labels and put a title, and we run this, and we get a very nice plot with a legend that shows what happens. And this is now, as we go down through the column, what happens to X's and what happens to Y's as we go down through the column, okay? And so the Y's are going in the sort of the opposite direction here to the X's, all right? So that's what that example looks like. So let's pop back over to our slides, and this shows the code, shows the file name, and shows the result in terms of our plot. Okay, so the last item that we're going to look at in this segment of the screencast for Bootcamp 2 is how to solve sets of nonlinear equations, nonlinear algebraic equations using Python. So the general formulation of this is shown here. Now we have n nonlinear equations in n unknowns, and we can represent this in a compact vector format as a vector of functions involving a vector of x's yielding a vector of zeros. And the common solution technique for this is called Newton's method, and it is expanded from Newton's method for a single equation. So we start with an initial estimate for our x's, initial estimates for however many equations we have. And then we have an iterative formula where we get a new estimate from the old x estimate using this adjustment. Now, this part here is just plugging our current estimates into our function equations. And then we use a matrix called a Jacobian matrix, which is shown down here, and its inverse times f of x, all right? Matrix multiply. So the Jacobian matrix is essentially the partial derivative of each equation, f1 through fn, with respect to each unknown. And there are times where calculating this derivative analytically is either difficult or impossible, in which case we use a finite difference approximation. This shows one way of doing it here, by perturbing each x by a little bit, delta, up and down, and dividing by 2 delta, and that gives us a numerical estimate of the Jacobian matrix. So if you go into a function that does this in Python that's built in, and you do not supply analytical Jacobian, it will use an approximate Jacobian to carry out this particular formula. Okay? So what we'll do here is we're going to set up a function which does this, all right? And we're actually going to do it first with our own code for the function. So let's pop back over and start a new script. And we will eventually need the NumPy module. So let me put that in. We won't use it right away. So I'm going to define a function called multi-newt. And what we're going to have as arguments, we're going to have the function, all right? Then we're going to have the function that computes j. Then we're going to have an array of our initial estimates. And then we're going to put in 3 additional arguments as keywords. One is going to be a convergence criterion, EA, and we'll put that in as 1 point e minus 7, 1 part in 10 to the 7th. We're going to put in a max iteration, all right, and we'll say that the default value of that is 30. And then we're going to put in something called a decelerator, where the default value of that is equal to 1.0. And I'll show you what that means in a moment here. So we're going to start out by saying our initial value for the calculations is called xold, and it is equal to our initial estimates. And then we're going to set up an iteration in a for loop that goes max ITR times. And again, ITER will start at 0, and it will be ranged in a list all the way up to max ITER minus 1. And so what we're going to do here is we're going to calculate an inverse matrix for J, which is going to be np.linalg.inv. That calculates the inverse for us. And then we need the J matrix. So we do J of xold. Now, what's happening there is that we've got xold, and this J is another function that we have to supply. So now we're supplying both f and j, all right, as we call this multi-newt function. And then we're going to say our new value of x, and this is just the Newton-Raphson formula, is equal to the old value of x minus, and then we bring in this little decel argument, which by default is equal to 1, so it doesn't play any role, times jinv period dot f of x old. So that implements the formula. Looking in here, f of x old evaluates our equations for the x old values, and then J inverse dot carries out matrix multiplication of J inverse times this f of x old. We multiply it by this decel, and I'll get to that in a moment, how we might change that. Subtract it away from x old to get x new. And then what we do is we say, well, how much did the solution change from this time to the last time? We call that xDEV. And then we say, well, how do we measure how big those deviations are? And the way we do that is we have a sum of squares calculation of xDEV dot xDEV. Now what that does, that essentially does xDEV transpose times xDEV. It's the sum of the squares of the deviations. Or also, in linear algebra terms, it's called an inner product. All right? And then we check and we say, if XERR is less than our convergence criterion up top, EA, all right, then we break out of this loop. Whoops. Otherwise, we assign the new values of x to x old, and we're going to go around and do this loop again. And then finally, when we're all done here, we return our result, and we can return it as, for instance, x new and ITER plus 1, where ITER plus 1 is the actual number of iterations that it took. So this is our little custom routine. Now we're going to try this on a simple set of equations, and then we'll show you how to do it using Python, and then we will take on an actual chemical engineering example. Okay, so we're going to come in here and we're going to define a function, f of x. And that function is going to start out, and we'll say Fn here starts out equal to NP zeros 2. All right, they're just two equations. And then we'll say Fn 0 is equal to x 0 squared plus x 1 squared minus 4. And then Fn 1 is going to be equal to x 0 times x 1 minus 1. Okay? And then we will just return those values. That's what f will get us up here. And then we need the Jacobian, all right? So we're going to def j of x. Our equations here are simple enough that we can actually compute the Jacobian analytically, derive it analytically, and compute it. So I'm going to start out here and say JAC is equal to NP dot zeros 2, 2. You'll notice when we do a two-dimensional one, we need an extra set of parentheses. We've mentioned that before. And then we're going to do JAC 0, 0. That's the partial of the first equation with respect to x0 is equal to 2 times x0. All right. JAC 0, 1. That's the partial of the first equation with respect to x1 is equal to 2 times x1. JAC 1, 0 is the partial of the second equation with respect to x1, with respect to x0, excuse me, which is just x1. And then the fourth element is JAC of 1, 1, and that is equal to x0, if we just look at those equations. And then we just need to return JAC, okay? And then we will get some initial estimates for x. X0 is equal to NP dot array. And we will try value of 0.5 and 1.4 for our initial estimates for our x's. And then we'll say that x solution and ITER, remember it returns 2 elements up here, is equal to multi-newt. Did I get that right? I think so. And it's F, J, and X0. So we're accepting the default arguments up here of these 3 last one. We're not changing that. And then what we're just going to do after that is we'll just print X SOLN and separately print ITER. And then we'll find out if we have any errors. All right. So before I do this, let me do a save as, and let me just call this 2 nonlinear equations. Let's try to run it. And it gives us the solution here of about 0.517 for the first x, 1.93 for the second, and it took 4 iterations to meet this pretty tight convergence criterion. So that's how that works. And let's pop back over to our slides and review that. So there's our function, and it's got some text here to describe. And what happens is the Newton's method has a tendency to go unstable. It's an open method that can be unstable, and convergence is not guaranteed. So often what you do, just a sec, let's get to where we were. Often what you do is you put in a decelerator that's less than 1, like 0.5 or 0.2 or 0.1, and that allows it to make not as abrupt a change in x old to get to x new, and it stabilizes the solution. And let's say decelerator less than 1, greater than 0 if needed for stability. And this shows the use of the dot method for matrix multiplication, and then again to compute the error criterion, and then it returns the latest solution and number of iterations. Okay? And then this is the example that we used at the top. It shows the Jacobian, which is very simply derived analytically, and then it shows what we put in, and the code is also duplicated in a file that's already in your collection, which is called multi-Newton. Okay? Okay, so what we're going to do now is we're going to take a look at a way to do this using a built-in Python function, and then we'll go on to our final example of this segment. So let us pop back over here, and let's see if we can find this equation. That is not it. Root function example. All right. So this is using a function available in the SciPy optimize module called root. And once again here, we define f of x exactly as we did before, where it calculates the equation errors for our two equations and returns them. This is exactly the same as we had before for our initial estimates, but now things are simplified because we do not provide the Jacobian, and we just get our result from the root function from optimize. And sorry for that interruption. We just get the answer. We do not supply the Jacobian, so the root function has to approximate the Jacobian numerically internally to its calculations. And then we produce our result. Now, the result here is actually an object that contains a fair amount of information. So if we just want the answer, we use the X component of the result object, and then we print here what result actually looks like when you display it. So let's run this. And so what we show here is that our solution is what we got with our own multi-newt example. And then the result object contains a lot of information. Solution converged, it's true. It gives the final function evaluation, X, the number of evaluations that was required, the final Jacobian value, and additional information that you can find by going in and getting the information on the root function. Okay, so that's what that looks like. If we pop back to our slides, this shows the result without supplying the Jacobian using the root function from SciPy optimize, and it shows the output that we just discussed. And this is the file where you can find the script that performs those calculations. Okay, on to our final example here in this segment, and we're going to take a look at steam-water equilibrium. This type of information would quite often be obtained from something called the steam tables in tabular form, but we can get a pretty good approximation using the ideal gas law and also using an Antoine equation for the vapor pressure of water. And that's these two equations here. And you'll note what we've got in terms of the ideal gas law. Ideal gas law said very quickly is PV equals nRT. And here N is equal to a mass divided by molecular weight, R the gas law constant, and T in Celsius converted to kelvins, PV equals nRT. And over here, we've got the vapor pressure as given by logarithmic by the Antoine equation. And so we have equations, constants here for the Antoine equation. You can get these in various places, including your material and energy textbook and Felder and Rousseau's book and elsewhere. And then additional information here, molecular weight and gas law constant for these units. We can then establish some operating conditions. These are arbitrary, but we've got mass of vapor being this value in terms of kilograms and the volume being this value in terms of cubic meters. And then we want to solve for P and T. We've got two nonlinear equations to solve for P and T. Okay? So if we analyze that further, we can write our equations out so that they're equal to 0. Here they are. And then we can look at what the Jacobian is, which we can actually get analytically here. Maybe a little bit painful, but the first one is pretty easy. The partial with respect to P is V. The partial with respect to T is minus M over MW times R. And then we can get the partial of these equation in terms of P here and in terms of T here. So we can do that analytically. And then we take a look at a practical situation, is that if we start to calculate values for these two equations, we find that the PV term using the units we've adopted could have a magnitude of about 10 to the 6th, whereas the second equation is closer to unity. This provides a bit of a scaling difficulty, so a practical approach to doing that is to do an arbitrary division of the first equation, in this case by 100,000, and then the equation errors are comparable. This is called scaling, and then it calls for an adjustment of the first equation in terms of a denominator. So that adjusts our Jacobian calculation. So let's pop over to Spider again. Let's close a couple of these files. And let's open one down here called Steam Equilibrium, EY. And it will show you how we do this. In this case, we did not implement the Jacobian, even though we showed that it could be calculated. We could do that with our multi-newt function. We can actually supply the Jacobian to root if we get into it. So we've got that. Here is our basic data that we had formulated. Here is our formulation of our two equations with our unknowns P and T being x0 and x1. We just changed their names here to make them more familiar. And then we've got our equation error as we did before, starting out with zeros and then calculating our two equations. And then we've got our basic data, our operating data, and we've got our estimates. And the first one is in pascals, so it's about 2 atmospheres. And then it shows 110 Celsius for that. And then we call the root function with our steam equivalent x. And here we go again, because we've got a couple of extra arguments, m and v, that have to get through from our main script through root to steam EQ. So we do that by our args equal m and v in parentheses, and then they will come in as root tries to evaluate that. And then we ask it to put that out. And we display the pressure here in kPa by dividing it by 1,000, dividing the pascals by 1,000. Okay, so let's run that. And it gives our solution as 216.9 and the temperature as 120.2 for that equilibrium. So let us come back to our slides and look at that script as we had it. Got some comments there to help you along with units, etc. And then, as I said, if we go in and do help on root, it would show you how we could actually have another function for the Jacobian analytically, and we could supply that to the root function so that it would not have to compute the Jacobian with a numerical approximation. Okay? So we're about to make a transition here, sort of a major transition in our workshop, where we're going to start looking at differential equations. So we're going to take this as the first screencast of our Bootcamp 2, and we'll take a pause, and then you'll see that we continue on the second screencast. So bye for now.